Okay, hello. Thanks for coming. Glad to see so many people are here. So I'm the new department head in the Department of Geosciences, so I'm here to introduce our speaker. I can say a few words about our speaker. It's one of the rare times I can actually say I've known the speaker since basically he was born. So I've known him for a long time. The interesting fact, so Dina pointed out, the last time this speaker gave a GeoOnsdag talk was during the pandemic in 2020. So there were two people in the audience, I think. You were one, and then Kiki Kruger was the other one. So there were two people in the audience. But what a nice change that we have a real audience this time instead of that. So a little bit about the speaker, best scientist in the world, okay? I mean, he comes originally from the United States, studied in the US, then he worked in France. So when he learned French and then spoke fluent French, but then that was only 2 years, moved back to the United States, forgot French, then moved to Norway next month, 23 years ago. Wow. So long time. So learned Norwegian, and I'm still learning Norwegian. So, I get corrected all the time. But he gets corrected all the time. Anyway, so warm welcome to our speaker, Joe LaCasce. Well, thank you, Joe. That's great. I really appreciate that. So we're talking about today about the Gulf Stream. So this is maybe one of the most known phenomenon in the ocean. So something that's and it's in the news all the time. So just to give you an example, let's see. Yep. I went on Google 2 days ago and I searched for Gulf Stream and immediately turned up a number of articles. These are some examples. This one from the Max Planck Institute, weaker ocean circulation could cost trillions. The other one, whatever BNT and Telenews is, it says Europe is headed for a mini ice age as AMOC tipping point paper approaches. Then, these are two articles that came out in The Guardian, not that far apart. The left one says, we don't know where the tipping point is, climate expert on potential collapse of the Atlantic circulation. And then the other one says, total collapse of vital Atlantic currents unlikely this century, study finds. Okay? So we have two completely different versions of this in the same newspaper. And then we have this one, which I thought was fun. We have this existential question. This comes from the University of Bergen. Does the Gulf Stream even exist? Okay, I mean, I thought we were further than that, but apparently there's some even raising the question about does it exist. So, given all that, you wouldn't be surprised that the public perception of the Gulf Stream looks something like this, right? This is the film The Day After Tomorrow, that suddenly in the middle of the night the Gulf Stream is going to collapse. It did happen pretty much overnight in this film. And within 2 days, New York was under this much snow, and the Statue of Liberty was buried up to her nose. Okay, so why? Why does this do? Okay, well, there are two articles that came out. These are not the only articles by any stretch about the Gulf Stream collapse, but there are two that made a big impact. One came out in 2021. The other one came out in 2023. The left one says, observation-based early warning signals of a collapse of the Atlantic meridional overturning circulation. The other one says, warning of forthcoming collapse of the Atlantic meridional overturning circulation. Well, when these two articles came out, there were a whole string of articles again in the news that printed these things. Often, you see a sort of a chain of events. They're often published in Nature and Science, okay? So these, more often Nature, I would say. Nature likes to do this, and then it gets picked up by these news agencies. Remember The Day After Tomorrow? An expert has predicted it could come true. Gulf Stream collapse as soon as 2025. So, these articles come out and have a big impact. And then immediately when this happens, people come up to me and say, is it true, Joe? Is the Gulf Stream about to collapse? And I'd say, well, not exactly, okay? But anyway, I'm going to go through why some of us don't necessarily believe all the hype here, okay? So today we're going to talk about specific questions. This is a crash course in oceanography, right? We got 40 minutes to learn all about it. Does the Gulf Stream exist? Okay, we'll take that one first, the existential question. Second, what is AMOC? People keep talking about AMOC. What is that? How is that different? Is that the Gulf Stream? Is it not the Gulf Stream? Confusion on that too. Are one or both of these systems about to shut down? Okay, is that going to happen? Then, here's a twist. What is the North Atlantic warming hole? Okay, this is something that gets discussed quite a bit, and this is often cited as a reason for Gulf Stream collapse. And last off, will we be buried in ice? Is there a new ice age coming? Okay, I heard this on the BBC. There was an interview a couple of weeks ago, and they were talking to one of these guys, and they said, I'm a little confused. We're talking about global warming, and you're talking about new ice age. How do those things go together? Great question, right? And in fact, the guy didn't even answer it very well. So we'll come back to that. All right. But let's start with the first question. Does the Gulf Stream exist? Well, there was no doubt in Benjamin Franklin's mind in 1770 when he drew this map of the Gulf Stream, right? So they knew back in 1770 if you were going to sail from North America to Europe, then the best way to do that was to sail in this fast-moving, what they thought of as a river in the ocean that was intensified off the coast of North America. So in fact, this map is, no offense to Benjamin, this map is a little imprecise. When you get out here, the current tends to spread out. But it is certainly very intense right off the coast of North America. He knew this in 1770. If you go back here, in fact, Ponce de Leon was exploring in the Caribbean in 1513, and he noticed that if he sailed from Puerto Rico up to St. Augustine, and down along the coast of Florida, he had the wind at his back, but the ship was barely moving. So he deduced that the current was moving against him. He was going right upstream of the Gulf Stream, not something that Benjamin Franklin would recommend doing. And so they knew already back then, so we're back over 500 years ago, that this current existed. All right. Now, what is this current? Well, it turns out the Gulf Stream is driven by the wind. So what is the wind-driven circulation? The talk that I gave during COVID, which is now 4 or 5 years ago, so my goodness, I talked about some of this. But a lot of these ideas actually began here in Scandinavia, but actually even more specifically in Norway. So in Norway, we have a lot of right to be proud about this because these ideas were developed. It started with this guy, you might know, Fridtjof Nansen, who was many things, a polar explorer, held the world record in the 1 mile ski race, crossed Greenland, but also was on his way to discover the North Pole. He was going to be the first person at the North Pole. When he was in the Arctic on his ship, the Fram, he noticed that when the wind was blowing this way, the ice drifted off to the right consistently, right? And he thought, that's interesting. And he was a naturalist. He wrote this down. And he had some ideas about how this happened. He went and talked to a friend of his, Willem Bjerknes, who is this building is named after, who was a professor in Bergen in meteorology. And he said, I've noticed this unusual thing about the ice. It keeps drifting off to the wind. Why? Well, Bjerknes had a very clever Swedish PhD student named Ekman. And he gave the problem to Ekman. Ekman developed a little model, which is drawn schematically here, which then demonstrated if you have some friction and you have the wind blowing at the surface, and it's going this way, the surface currents are indeed off to the right, and then the currents, as you go down with depth, they turn to the right. And so when you integrate over the top, the transport is actually off to the right in the northern hemisphere. So it's what we now call Ekman transport. And I always say this is a good lesson to any of you, potential PhD students. Get a good advisor like Willem Bjerknes, right? And because now we have Ekman transport, Ekman spirals, Ekman pumping, which I'll show you in a minute. Anyway, another Norwegian was this guy who may not be as well known as Bjerknes. This is Harald Sverdrup, and he was a Norwegian researcher in the middle of the 20th century. And he realized that Ekman transport, if you look at what happens on large scales, ocean basin scales, that this can drive a large-scale flow. So he derived, I'm only going to show two equations. That's unusual, but I'm only showing two. This is one of them. And the reason I'm showing is it's so simple, right? This is a really, really, well, okay. I mean, beauty's in the eye of the beholder, but this is about as simple as they get. This basically says that this is the wind term, that the ocean circulation goes like the gradient of the wind, okay? It's the curl of the wind. But it gives us a way of predicting what the large-scale circulation looks like. So this is what the winds are doing to the ocean. This is what we call Ekman pumping. So if you take the winds, the curl of the winds, the gradients of the winds, it looks like this. And what you have is you have these large regions. These are called the subtropical gyres, where you have negative regions. And up here, subpolar gyres, where it's positive, right? And so you get a circulation that comes from that. And you take Sverdrup's relation, you take those wind fields and you plug them in and you predict structures which look like this. So this is the Pacific, this is the North Pacific and the South Pacific, and you have these large-scale gyre structures, right? Really simple, wonderful theory, and it predicts this. And this is basically what we see. So if you are sailing out in the middle of the South Pacific, you will see that you have this northward flow, gradual northward flow. If you're in the North Pacific, you see you have this southward flow, and that's predicted by Sverdrup's relation. Okay, but one thing Sverdrup didn't get was what Benjamin Franklin picked out, why is that current, why do you get this intense current on the western side of the basin? This was a puzzle for hundreds of years until this guy came along. So this is Henry Stommel. So this is, in oceanography, this is the father of dynamical oceanography. This is basically our Einstein. He had a wonderfully creative guy. He was doing a lab experiment sitting on a rotating table. Don't try that at home. But he showed another model where he showed basically that this is what you get, that currents are intensified he demonstrated this on the western side of the basin. So when you look, for example, in the North Atlantic, you have this western intensified current, that's the Gulf Stream. And on the western side of the Pacific, you have their version. If you're in Japan, you don't talk about the Gulf Stream, you talk about the Kuroshio, because the Kuroshio is their big current, right? If you're in Australia, you don't talk about either of those, you talk about the East Australian current. And they're all what we call western boundary currents, right? And they're forced by the winds. Okay. So that's the background for wind-driven circulation. Now, this was an opinion piece that was written by a professor of mine who's well known for being opinionated. Okay, his name is Carl Wunsch, so he's a great guy. And this is from 2004 in response to an article which had been published in Nature. Gulf Stream probe for early warnings of system failure. Okay, again, 2004. Carl wrote this article where he said Gulf Stream is safe as long as the wind blows and the Earth turns, right? So as long as neither one of those things stop, then we're not going to see the Gulf Stream vanish, right? So he did this, and this got some attention, but you see it didn't have any effect, because here we are, 21 years later, and we still have these collapsing Gulf Stream articles coming out in Nature. Okay, well, one thing, though, that Carl didn't consider in this paper is there's a second component of the ocean circulation, and that is something we call the buoyancy-driven circulation. So this is what happens because the density of the ocean, of seawater, is not the same everywhere. It varies with location. It's more where you have cold water at the higher latitudes and you have warmer water at the low latitudes. Those density contrasts also have an associated flow. So I'm going to explain that. Now, the thinking about this also goes back to Henry Stommel. So here he is again, doing some work in the early 60s. And Stommel was envisioning what would happen if you had, at the deep part of the ocean, so say in the lower 4,000 meters of the ocean, if you have these regions where you have, because they already knew this might be happening, you had convection, you have deep sinking of these surface waters down at the bottom. So Stommel said, well, let's imagine I have a source here, source down here. What kind of circulation would I get? Well, it's quite complicated. You get gyres that look like Sverdrup gyres in all these different basins, but this is down at the bottom. And you get these western boundary currents. Okay, so just like the Gulf Stream, except at the bottom of the ocean. So Stommel in 1960 predicted, you know what, there's probably a current going in the opposite direction, going from north to south underneath the Gulf Stream. This had never been observed. All right. But it was observed shortly after. So he talked to this guy. I always put this picture in because I love this picture. He was a British researcher named John Swallow, delightful guy. Here he is on the deck. This is back in the also early 1960s. Here he is on the deck wearing his tweed jacket and his tie. He is British after all. And I love the cat is watching here too, as he prepares this float to be deployed in the ocean. They went out and indeed they measured this, and there it is. So there's Stommel's, what's now known as the deep western boundary current. Okay, this is the deep portion of this flow underneath the Gulf Stream. That's the Gulf Stream up on top. So predicted again by a very simple theory, and there it was flowing south. They found this. So there was a lot of excitement. This doesn't happen very often, that you have a theory that predates the observations. It doesn't happen in our field very often. Okay, but so Stommel's solution, though, is still very idealized because, what he's saying is, well, let's imagine we have convection. It doesn't actually model the surface of the ocean. But there were a number of studies that followed where people looked at what kind of circulation you would get if you just did heating and cooling, okay? So, and this one example over here, this is from a paper written by Ada, who's sitting over there, okay, who's looking at her computer. All right, that's actually a figure that she drew up here. And this is a very simple square ocean. So this is what we often study, shoebox type of ocean. We have heating down here, low latitudes, and cooling up here. And what do you see? Well, you see this funny thing that it's not like the flow is all going up to the north to sink. What actually happens is a lot of the flow is going from west to east, so just from this heating. Well, that also can be predicted with a very simple formula. This is something that's known as the thermal wind relation. And thermal wind is our way of understanding how the ocean responds to density contrast. Rho here is the seawater density, and if I take a derivative of that, that's how that density is changing with latitude. And that is associated with a flow. So this U flow is the east-west flow. So if I have a density contrast north-south, I'm going to get a flow to the east or the west. Okay, those two things go together. Now, thermal wind, again, is something that was familiar in the meteorology before we got to oceanography. So, this one is a little more, if you've ever been on a plane, you've experienced this. This is the atmosphere. At low latitudes, you have warm air, so down near the equator, and of course, it's cold up at the pole. So you have a density contrast in the atmosphere. You have heavy air here and heavy air here, lighter air here. So there's a contrast. And associated with that density contrast, you get a flow. That's called the jet stream. Okay, that's why when you fly from North America to Europe, it takes an hour less than it does to fly in the opposite direction, because a lot of times the planes will fly with the jet stream doing that. That jet stream exists because of the density contrast. All right, that's known as thermal wind. The same thing applies to the Gulf Stream. You have warm water down here, cold water up here, so there's a density contrast. And the Gulf Stream is not a river in the ocean. It's right on it's a barrier between the warm and the cold water, okay? And that density contrast has a flow associated with it, all right? So that's thermal wind. Again, a very simple idea to understand. Now, so Ada, and again, giving some advertising to Ada over here, she ran a model a few years ago when she was a PhD student, where she took the whole ocean, right, and ran a big model, and then turned off the winds, okay, just did heating at the low latitudes and cooling at the high latitudes, and to see what would it look like, okay? Well, here's what the surface circulation looks like in a simulation like that. You see this west to east kind of flow. That's thermal wind, right? But on top of that, you get these western boundary currents. So you get one over here, you get one over here, you get one down here, and one down here, right? So even with zero winds, you're getting something that looks like western boundary currents. Well, if you compare those currents with what we actually observe, it looks pretty similar, right? There's the Gulf Stream, and there's a Gulf Stream. There is a Kuroshio, there's a Kuroshio. Here's the East Australian current. Here is that's a Malvinas current. That's I forget what that one's called. Something, a Brazil current, maybe, something. But anyway, a lot of this looks very similar to what you see in the ocean. Okay, what does this mean? Well, this means we've got two things going on. We have a wind-driven circulation giving us western boundary currents, plus we have buoyancy forcing, density forcing, which are giving us western boundary currents. These two things are right on top of each other, right? So over here, in this region over here, we have a wind-driven Gulf Stream and we have a buoyancy-driven Gulf Stream, both of those things, okay? And so that's why this gets a little confusing. Sometimes people call it the Gulf Stream. We don't tend to do that. In oceanography, we tend to refer to the part that goes north as the North Atlantic Current. Actually, it's something funny. When it crosses the Denmark Straits, the Norwegians take control of this, and then they call it the Norwegian Current, okay, or the Norwegian. So that's our current, right? So off the coast of Norway, it's the Norwegian Atlantic Current. South of Iceland, that's known as the North Atlantic Current. And then that is actually superimposed on the Gulf Stream. So you have these two things happening together. Okay, so let's answer a couple of our questions. Question one, does the Gulf Stream exist? You bet it exists, okay? And the Gulf Stream, what we call the Gulf Stream, is the wind-driven part. So, and it's driven by the winds, and like Carl said, it's not going anywhere. As long as the winds are blowing, we're gonna have a Gulf Stream. What is AMOC? Well, AMOC is the Atlantic Meridional Overturning Circulation, and that is shorthand for the buoyancy-driven part of the flow, which is primarily in the North Atlantic. So what we know is that there's a strong component which is in the North Atlantic. It's because we get a lot of the deep water formation that happens in the Atlantic Ocean. So AMOC, when you see AMOC, that means it's this Atlantic, and you could think of it as the buoyancy-driven circulation. Okay. So, are they about to shut down? One or both. Two, what is the warming hole? And three, are we going to be buried in ice? All right. Here are observations. So people have been out doing this. Again, we have these articles coming out. We're nearing a tipping point. It's weakened dramatically in the last 100 years, blah, blah, blah. Okay, these are the actual observations. So there are several programs. One is a European program which is called RAPID, where they're monitoring at 26 degrees north across the Atlantic basin. Here's another one which is further south. This is called the MOVE array, and there's one to the even further north which is called OSNAP. All right, and in all cases they're monitoring flow near the western boundary to see how much of the ocean circulation is still going on. Has it changed? Well, these are not very long time series. Most of these things have only gone for about 20, 25 years. But up to this point, there is really no evidence for any weakening of these flows. There was something that happened. This is in the rapid array. If you look over here, you see suddenly it goes, whoop, it falls. An oceanographer, a respected oceanographer, went, oh my gosh, the Gulf Stream is dying. Wrote an article, published it in Nature. Well. And what happened? 1 year later, it bounced back again, you know? So this, you could see it here, right? So, or right afterwards, it came back up again, and now it's been recovering. So there is year-to-year variability in AMOC, in the ocean circulation. And you see it up here too in this MOVE array. You can see this falling down like this. But there's no trend that we see so far. And when they do reconstructions of this back further, these are 60-year reconstructions. Again, you don't see any long-term trends. Not yet. Okay, so we can't, so if anyone says, oh, we see it happening, we don't. Okay, we do not have any convincing evidence yet that it's happening. Okay, now, but you can ask, what's going to happen in the future? Well, obviously we don't know. We don't have observations from the future, right? We're not Doctor Who, right? So what we need to do is we need to use models, right? So we need to use climate models. Now, climate models are actually quite good at reproducing what's already happened. We call this a hindcast, so going backwards in time, and they're actually quite good at doing that. So we have faith that they're capturing some of the essential processes that are going on. Remember, we can express the wind-driven circulation and the buoyancy-driven circulation with very, very simple balances. And the models tend to capture these things pretty well. Okay, so every few years, the Intergovernmental Panel for Climate Change, IPCC, puts out a report. So Terry has been involved with this, and a number of people maybe also in this room have been involved with these. They come out with these reports, and they say, this is the state of the climate, this is what's happening. And they rely on these models to say how things are going to change out to 2100 or so, all right? Now, when you look at what they usually do is they take these models and they use what we call different scenarios. So they have, a large amount of CO2 that's being put in the atmosphere, or sort of CO2 that's been put in the atmosphere and then gradually damped down, or even cases where they're removing CO2 from the atmosphere. So we have these different scenarios. But in a lot of these things, this is the measure of the Atlantic of this AMOC, and you can see that in many cases you see a decline over the next 100 years. So the models are suggesting that we are having a decline taken together. We looked into this a few years ago, so this is with a student of mine, Gaurav Madan, who's now in England, and we were looking at my favorite simulation. Now this sounds grim, right? This sounds like the most nihilistic of these simulations, but this is a case where they quadruple CO2 in the atmosphere overnight. Okay, not a very realistic simulation, but very useful for studying how, for instance, the ocean responds to drastic climate change. Okay, you suddenly quadruple CO2. What happens? Well, this is, again, a measure of the overturning circulation. And so here it is, and we've normalized it, starts at 1. And you can see that it's falling down. By about 60 years, it's decreased. All right. Now, has it collapsed? Okay. Well, it depends on what you mean by collapse. It's certainly weakened. In some cases, it's gone down by almost 80%, right? But in some cases, it's only decreased by 15%, right? So different models exhibit different weakening of this circulation, right? On average, they tend to decrease by about 55%. And this is under this really extreme forcing, all right? So it doesn't look like a tipping point is something where you'd expect a drastic change all of a sudden. This is more of a gradual change, and the models show different responses. So I don't really think that this is something that we would characterize as a tipping point. This is much more like you're changing a dial, you're changing that. Now, why does AMOC weaken? All right, well, we went through and we looked at various different possible causes, change in the winds in the northern hemisphere, changes in the winds in the southern hemisphere. All of these things have been pointed out as possible reasons for a decrease in this. Turns out the main cause is a change in density. So what you have here is this is a change in density in this 4 times CO2 compared to a case where you don't increase 4 times CO2. And what this red is saying is that the density is actually reduced. So we have now lighter water in this 4 times CO2. Now, originally what we were thinking was, well, of course you have lighter water. You're making the planet a lot warmer. So you're warming up the northern regions, and that's making things less dense and north of the thing. That was wrong, okay? It wasn't. So when you look at the change in the density due to temperature, in fact, actually, it's the opposite sign. You get some cooling, which happens here. That's the warming hole. I'm going to talk about that in a minute. But you also have some warming, which happens down here. So in fact, this is actually increasing the density contrast. So this is lighter, this is heavier, so the density contrast is increasing. But if you look at this is the change due to salinity. What's happened in these simulations is that when you quadruple CO2, you get something that's called Arctic amplification. So what you're doing, Arctic amplification means that the pole is warming up, the Arctic is warming up much faster than the rest of the planet. So we think it's on the order 2 to 4 times faster. So at Svalbard, for example, they're seeing much more dramatic changes than they are further south, all right? So that's Arctic amplification. And due to this, Arctic amplification has resulted in widespread melting. So we're seeing the sea ice disappear. This happens within a year or two in this simulation. It's very, very dramatic. All that melted sea ice plus runoff from fresh water enters the North Atlantic. So you have this fresh water coming in this tongue, and it particularly is coming in here just north of the Gulf Stream. When you combine these two things, it's the salinity that wins. Okay, and we have reasons for thinking this, that salinity dominates density contrasts, okay, when you're at higher latitudes. So it's the salinity which gives us this. So Down in this part, there's not much of a net change, but up here, fresh water dominates the change in the density, and that change in density contrast gives you a weaker Gulf Stream, so a weaker North Atlantic flow. So here's the density gradient. What we did is we looked at 42 different models, so Goroff has numbered them all here. All right, 46, there's 46, or 64. No, I guess they just have different numbers. I think there's 42. And he did a correlation between the change in density and AMOC, and you can see it's very well correlated. Well, it's reasonably well correlated, significantly correlated anyway, and it's due to salinity. So we see a strong dependence on salinity. There are always some models which are outliers. If you remove a couple of these guys, 2 models, in fact, if you remove these, then all of a sudden your correlations are up around 0.8 or so, something like that. And here's an example of this. When you break down all the different contributions, sea ice is really the big one in this simulation, but also runoff is another one. And you put it all together, this is the, over here, this is the decline in the freshwater. So this decline in the freshwater fluxes, and this is the decline in AMOC, and those two things go hand in hand. So basically, as you're melting and you're dumping all this fresh water in, then you're weakening the Gulf Stream. Okay. All right. Back to these papers. So they're claiming now that AMOC is weakening, Gulf Stream is weakening now. How do they come about this, right? We've already seen, we don't have direct evidence in situ velocities that show the change in AMOC. So how are they getting this? Well, what they're doing is they use, in both of these papers, they use a rather simple climate model. Here's one, okay? So that's their climate model, right? It's a first order, for those who are in the know, it's a first order stochastic differential equation, right? Right? And so you have a decay term, you have a noise term, and you have this. This is basically the model that they're using. And what they do is they take indices. So they look at how different parts of the ocean are changing. And in particular, the one they like is right up here. It's south of Greenland, and it's this region which has a big blue blob right up here. If you look at the ocean here in this picture, it's mostly red, it's mostly warming. But there's this one spot up here which is not warming, it's cooling, okay? That is known as the North Atlantic warming hole. I'll say about that in a second. This is the other study, same thing, slightly more complicated model, climate model. They've got a couple extra terms, still a first order stochastic differential equation, right? But their measure up here is this region of the ocean, right, in what's called the subpolar gyre. And they're using that to then deduce, comparing with this model of theirs, to deduce that, yes, there's a collapse that's going on. Okay. This is actually in Wikipedia. It's not listed in Wikipedia as the warming hole. In there it's called the cold blob. Okay, so it's a cold, right, a very descriptive thing. And this is the residual surface temperature relative to 1980. Indeed, this region of the ocean is cooling. We see this in observations, okay? Now, what some people have suggested is that cooling part of the ocean is a signal that the heat transport in the Gulf Stream or the North Atlantic current is dying, okay? So that is why. So you have less warm water coming in from low latitudes, and the whole thing is cooling off. You also see this down here, by the way. There's a cooling in the Southern Ocean, too. But that's not discussed as much. This one is the big focus of this, right? Okay. And when you look at this is in one of our simulations here. Indeed, these two things go hand in hand. So the blue curve here is a measure of AMOC, of the ocean circulation. This is from 1600 up to 2100. You see we get up to about 2000, slight increase, and then vroom, it collapses. Well, it falls, it's decreasing by some 55%. But this red curve is the temperature anomaly in that warming hole. And you can see that's going hand in hand in that. All right. So yeah, it looks like, oh yeah, those two things go together, right? Well, okay. Do we see it in this observations? You know, I showed you another thing. These are 4 different data sets, and indeed, this shows up in all the different data sets. Here's a blue region over here. These are reanalysis data sets where we take data and put it together with a model and do this, okay? So the SST is changing all these things. So this is a feature, it really is, and it's there now, okay? We think it's formed really in about the last 10 years, but it's definitely there now. Okay, but we're writing a paper about this now, too. When you look at the salinity in that same region, well, lo and behold, there's a salinity anomaly there as well. So that water, which is cold, is also fresh, okay? Now, what you do is, if you look at this, you look at simulations, what you can do is you can track this. This fresh water comes in here, and then you can track it right along here. It comes in north of the Gulf Stream and then settles in the subpolar gyre. And so which explains its structure. Why is it so localized? Why is it there exactly? Well, it's being advected in by the ocean. Temperature changes usually happen over much larger areas because it's affected by the atmosphere. This stuff is being advected in. Well, what happens is this fresh water then mixes. And so mixing processes in the ocean like to reduce density gradients. So if you look at the density here, there's almost no signature of the warming hole. So the warming hole, or the cold blob, is not a dense blob, okay, or a light blob. It's nothing like that. It doesn't show up. Where it does show up is in something that we call, oceanographers call spice. Okay, that's a great colorful name, right? But spice is like density, except that temperature and salinity work together instead of working against each other. And this shows up very clearly. So this is what we mean, that this structure is most likely not a cold anomaly. It should not be cold blob in Wikipedia. It should be fresh blob. Okay, it's a freshwater anomaly. And it's been subjected to oceanic mixing. Okay, so this is not really a signature that AMOC heat transport is dying. It's something else. Now, if you go and look at this, again, here's what I just showed with this is the SST from in the warming hole, and this is also the strength of the overturning. And this blue one is the freshwater content that is coming out of the Arctic. And you can see this is declining down. This is, well, the freshwater fluxes are declining. And this happens about 10 years before the other one. So what's happening is the warming hole is intensifying, and the AMOC is weakening in these simulations due to freshwater. So freshwater is the key. Okay, before I did this, I did not realize how important sea ice is, right? And land ice and all these things. Enormously important because it directly impacts the ocean circulation. Okay, last question. New ice age? So sometimes this paper gets picked out quite a bit. This came out in 2017. And this was a study where they looked at this. And this is temperature over the whole Earth. And look at that region up here. Okay? If this is where it were to happen, we would be quite a bit cooler. Okay? This is a temperature anomalies. This is like 2 to 3 degrees colder. Okay? And this is often pointed to saying, okay, not just simple models of the Gulf Stream, but fully complex models too. All right? But this model, there were some funny things that they did. They made some flux adjustments, and they did this. It wasn't a completely self-consistent simulation. When you look at the IPCC scenarios, here we have different ones. This is 1.5 degrees of warming, 2 degrees of warming, 3, 4 degrees of warming. You can sometimes see evidence of this warming hole right over the Atlantic, right? Right over the ocean. But everywhere else, it is hot, okay? So it is hot. So we don't need to worry about a new ice age. These changes are happening precisely because it's getting hot at high latitudes, not cold, right? And so there's no danger of an ice age. Okay, so now we've answered all our questions. Third question, are one or both about to shut down? AMOC has not weakened yet in the observations, but what we see is due to this freshwater input, it probably will weaken in the next, up until 2100, it's going to be weakening. What is the North Atlantic warming hole? It's actually a fresh blob. It's a freshwater anomaly, and that results due to ocean mixing, okay? It does not result from AMOC weakening, but both of them, both AMOC and the freshwater in the warming hole, are responding to the same forcing, which is this fresh water. So in a way, it's not wrong to say, oh, we use the warming hole as an indicator, okay? But it's not a cause and effect. They're both responding to the same forcing. And will we be buried in ice? That's not what we need to worry about, okay? AMOC weakening occurs because of Arctic amplification, all right? It's gonna get hotter here. So we have to get used to this beautiful weather, okay? So, tack. Thank you, Joe. That was very interesting. Best talk I've ever seen. Do we have any questions from the audience?
Thanks a lot, Joe. It was indeed very interesting. I was just wondering, have you assessed where the major part of this fresh water comes from?
Yeah, that's a great question. We get that every time we put it in a paper, right? You know, because that's exactly what people want to know. Is in these simulations, the big component's coming from sea ice, okay? But that said, in the IPCC, they don't have active ice sheets. So Greenland doesn't have an active ice sheet. So there is fresh water that's coming off of Greenland, but it's runoff. So we don't have this component of that too. What will that do when we add this in? We think it's going to make it even worse because you're going to have even more fresh water coming in. But in these simulations, the two big ones are sea ice melt and freshwater runoff from the continent, those two things. Yeah, Greenland, but also actually Canada too. Quite a bit coming in from there as well. It runs down, the freshwater runs down along the boundary, the western boundary. So Labrador Sea, Baffin Bay, this area, comes down around and then enters north of the Gulf Stream. So that's the thing. But there's still, I mean, sorting out that freshwater budget is really important to do and needs to be done. Yeah. Yeah.
Hello, thank you, nice talk. What if you go a bit further back in time when the last glacial maximum was, and then we had also this really warming period, where suddenly there was like younger dryas and so events. So there's no danger of these type of events where really like large lakes and fresh water, of course, come into the ocean.
Yeah, that's a good question too. So what I'm saying now is really talking about what's happening under anthropogenic forcing, right? So when we're really perturbing the system with CO2, we can think of it, we're running our little volcano experiment here by dumping all the CO2 into the atmosphere and then increasing the temperatures. But in previous times, in the glacial periods, you do have these swings that go back and forth due to Milankovitch cycles and so forth. And then you do see changes in ice cover. So ice can expand and ice can retreat. Most likely what's happening is that AMOC, the ocean heat transport, is shrinking and growing along with those cycles. But this way of diagnosing it in terms of the density difference hasn't really been done yet. So this is something we need to look at as well. We need to go back in time and then actually go into these simulations that show this. There's a simulation that they run in Denmark. There's a guy in Denmark who runs these simulations that does show glacial cycles, and we need to go in and analyze that and see what's happening in those. But in those cases, yes, you can have an ice age. Of course, we know you have ice ages, and so that does happen. But those are what we would characterize as more climatic swings, rather as opposed to these responses to really drastic forcing. Yeah. Valerie?
All these currents are on the east coast. I guess this has to do with the rotation of the Earth, but I don't think you said so. I would like you to confirm maybe. Why are they always on this side?
Great question. So this is something that we have actually on it's one of the problems in the dynamics course that I teach. I said, because there was a movie, Superman, the first Superman movie, and what Superman did was Lois Lane died, right? So it was very tragic, and Superman was really was torn up about it. So he flew around the planet, and he made the rotation direction change, so go in the opposite direction. And of course, what that did was it reversed time. So time went backwards, and then Lois came back to life again, right? Okay. So I had that as a question in our, so you change the sign of rotation, what happens to the Gulf Stream? The Gulf Stream jumps over to Europe at that point. Okay, you can prove this. So if the rotation was changed, it would go over there. Yes, it's due to two things. One, it's due to rotation, so that the fact that we have western boundary currents, but it's also due to the fact that if you are at different latitudes, you feel the rotation differently. You feel there's a maximum up at the pole, and then the net effect of rotation is not felt at the equator. So as you go up at higher latitudes, rotation becomes more and more important. And it's actually that gradient in the rotation rate which is responsible for this western intensification. Yeah, so it's a subtle effect. Yeah. Okay. Great, thanks for coming. Are we supposed to, okay, so this is, thanks again. This is the last of the GeoOnsdag talks for this spring, so we'll resume again in the fall. And if anyone would like to volunteer to give some, we've got a list that we're making, and so come talk to me and I'll get you on the list, and that'd be great. So thank you.